easy bit. So the next concept is binomial random variable. So the next concept name is binomial random variable. So we have discussed in the previous class about Gaussian random variable and uniform random variable. Now today we will discuss about the Gaussian random variable. So let assume 0 less than p less than 1. That means the what it tells you is the probability is always lies between 0 and 1. And let n equal to capital N equal to 1, 2, 3 and so on and so on. Then the function fx of x equal to sigma k equal to 0 to infinity p power k 1 minus p whole power n minus k. Here you are having nck and delta of x minus k. Delta of x minus k is called is called binomial density function. Binomial density function. So let p 0 less than p less than or equal to 1 and n equal to 1, 2, 3 and so on. And the function fx of x is equal to summation k equal to 0 to infinity. Here it is nck p power k 1 minus p whole power n minus k. Delta of x minus k is called binomial density function. Here nck is equal to n factorial divided by n minus k factorial into k factorial. This we already know. So we already know NCR. NCR is equal to n factorial by n minus r factorial into r factorial, right? So in the same way, NCK is equal to n factorial by n minus k factorial into k factorial. Now this is probability density function. So if you want to find out the probability distribution function, the probability distribution function of this binomial random variable is represented by f x of x is equal to, so summation same k equal to 0 to infinity nck p power k 1 minus p whole power n minus k u of x minus k so where u is step function a step signal. In the same way, in the numerator, in the above example, delta is impulse function. So how we get delta from, so the expression for probability distribution function density function is almost same, but only a small difference if you consider, if you see this. So entire this part from here to here, everything is same in probability distribution function and density function. Only difference is this delta. So here delta is replaced with what? In this case, delta is replaced with u. That means we already know the relationship between probability distribution function and density function. So if you integrate the density function, you will get the distribution function. That means the integration of impulse function is becomes what? It is step function. We already know the integration of impulse function is always equal to 1. So this is the explanation of binomial random variable. So if ever they ask you about the any random variable, you have to write density function and distribution function. Now we'll see one problem on this. So it is like this. So they gave you n equal to 6, capital N equal to 6 in this case, and probability p equal to 0.25. probability 0.25. So what they ask you is find out find distribution function, sorry, density function, distribution function, and sketch and their figures, and sketch fx of x and capital Fx of x. So this is the problem. So this is the one of the problem on binomial distribution function. So coming to the binomial density function, we already know that. Fx of x equal to summation k equal to 0 to infinity nck p power k 1 minus p whole power n minus k delta of x minus k, delta of x minus k. Okay, so as the value of n equal to 6, so we have a chance of k equal to 0 to 6 only. Why? Because we have 6c6, we don't have 6. Suppose n equal to 6 here now, 6c, if you put k equal to 7, 6c7, so there is no chance of 6c7. So that's why it is n equal to 6 always. So 6c k, p means 0.25 whole power k, 1 minus p means 0.75 whole power 6 minus k into delta of x minus k, delta of x minus k. So what we have to do now is we have to expand this one. So which is equal to, if k equal to 0, k equal to 0 means 6c0, 6c0 means 1, 0.25 whole power 0 is equal to 1, and 0.75 whole power 6 minus 0, that means 0.75 whole power 6 into delta of x is the first one when k equal to 0. If you substitute k equal to 1, it is 6c1.25 into 0.75 whole square into delta of x minus 1. So and so on. If you substitute 2, 3, 3, 4, 5, and if you substitute 6, it is 66. 66 is equal to 1, and 0.25 whole power 6, 0.75 whole power 6 minus 6 is equal to 0. Sorry, is equal to 0. That means 0.75 whole power 0 equal to 1, and delta of x minus 6. Delta of x minus 6. And if you plot this impulse function, it is like this. The plotting of impulse function and density function is very important. So here you are having a value at 0, 1, 2, 3, 4, 5, 6. And all the above ones are all the above are what? Impulse function. That means you are getting impulses at x equal to 0, x equal to 1. That means here x equal to, x equal to 3, x equal to 4, x equal to 5, x equal to 6. That means your density function is like this. It is it is in steps form. That is 1, 2, 3, 4, 5, 6, 7. So these values are different. So these values can be find out from the above expression. So this value is 0.75 whole power 6. At the origin, it have a value of 0.75 whole power 6, and at the at n equal to, at x equal to 6, you have what? 0.25 whole power 6. So likewise, you can draw the distribution, density function of a binomial random variable. So if you want to plot the same with density function, sorry, distribution function. So distribution function is fx of x. It is x. So what we will do is, so the distribution function is, it is a slowly increasing function, slowly increasing function. That means it is slowly stepwise increases, stepwise increases at every value of, at every value of 0. I mean, at 0 it has one value. At 1 it has 0 plus 1. That means added. At 2 it has total value of 0, 1 plus 1 and 2. At 3 it has 0, 1, 2, 3 and value. At 6 it has a value of 1. Why? Because the maximum value of your step function is always equal to 1. That means if you add all the probabilities from 0 to 6, you will get totally a value of 1. A value of 1. That's why you already know that one the probability from the this one property of distribution function, we know that it is fx of infinity is always equal to 1. So in the same way here, you get fx of infinity is equal to 1, right? That's why if you draw the probability distribution function, so it is like this. It is a staircase function. Whatever may be the random variable, any type of random variable, it is always an increasing function only. Slowly it is increases, and at the final value it approaches to value of, so this value is always is equal to 1. So from there it does not increase. Why? Because the value of fx of x at infinity is equal to 1. So this we can already know from the properties of mm, uh, from the properties of probability distribution function. So this is what about the binomial density function. And I mean binomial random variable, its density function, its distribution function. One example problem on binomial random variable, and how to plot the density function, and afterwards how to plot the distribution function. So the next random variable is exponential random variable. So the next random variable is exponential random variable. So exponential random variable. So the density function and distribution functions of exponential random variable is given by, see, if fx of x equal to 1 by b e power minus of x minus a by b for x greater than a, 0 for x less than b, for x less than a, this is also x less than a. So this is the density function of exponential random variable. So how it is looks like, so fx of x equal to 1 by b e power minus of x minus a by b for x greater than a, and 0 for x less than a, x less than a. So it is x greater than or equal to a. Now see, if I want to plot this exponential random variable, it is like this. It is, so the curve of exponential random variable is like this, fx of x, and this is x, this is x. If you see, if you analyze this one, if you put x equal to a, if you put x equal to a, that means, suppose I am assuming my a is here, and according to the definition, for x less than a, it is always equal to 0. That means here on, from till here it is always equal to 0. For x greater than or equal to a, it is having expression. Suppose put x equal to a, If we put x equal to a, e power, it becomes 1 by b into e power minus of a minus a divided by b. That means 1 by b into e power 0. That is e power 0 equal to 1. That means 1 by b. That is at a it has a value of, it has a value of it has a value of 1 by b here at x equal to a, at x equal to a. From there onwards, if you increase the value of a, the exponential value is the power of exponential, the negative power of exponential slowly increases. So the value is slowly decreases. The value is slowly decreases and approaches to 0 as the value of x tends to infinity. Why? Because if you put x equal to infinity, it becomes e power minus infinity. So that means e power minus infinity is equal to 0, and the value is equal to 1 by b equal to 0 is equal to 0. 1 by b into 0 is equal to 0. So this is the figure of of probability density function of a exponential random variable. Exponential random variable. Now moving on to the next one. The next one is density function is over. Now next one is distribution function of exponential random variable. So in the same way, the distribution function of exponential random variable is equal to 1 minus e power minus x minus a by b for x greater than or equal to a, 0 for x less than a, 0 for x less than. So this is the expression of exponential random variable distribution function. In the same way, if you plot the probability distribution function of this function, so it is like this. It is like this. Here it is. So here it is fx of x, and it is x. So if you plot this one, so as you know, if you put x equal to a here, if you put x equal to a here, so starts from x equal to a, e power minus of a minus a, that means e power 0. E power 0 is equal to 1, that means 1 minus 1 is equal to 0. That means it has a value. Suppose let us write you put x equal to a in this expression, then it becomes 1 minus e power minus of a minus a divided by b. That means it is equal to 1 minus e power 0. That means 1 minus 1, which is equal to 0. So it starts at a value of 0, at x equal to a, So here it has a value of x 0. So as the value of a increases, slowly it increases, and at a value of x equal to infinity, it obtained a value of 1. So at x equal to y, because we already know that distribution function maximum value is equal to 1. Maximum value is equal to 1. This is about the this is about the this one, exponential random variable density function, distribution function, their figures. Okay. So the next random variable is Rayleigh random variable. Rayleigh Rayleigh random variable. Okay. So similarly, in the same case, here we just take out the density functions and distribution functions formulas. So the density function of Rayleigh random variable is given by 2 by b into x minus a e power minus of x minus a whole square by b for x greater than or equal to a. For x greater than or equal to a, 0 for x less than a. 0 for x less than a. So this is the expression for probability density function of Rayleigh random variable. So if you plot the probability density function of Rayleigh random variable, it looks like this. So it has so if you s- as you see here in the density function, so in the exponential, you are having x minus a whole square by b, x minus a whole square by b. So if you the expression if afterwards if you sorry if you plot this one, it is like this. It is like this, and it has a maximum value of 8 at x equal to a plus root b by 2, a plus root b by 2, and at x equal to a plus root b by 2, its value is 0.607. Sorry, its value is 0.607 root over 2 by 2 by b. So you know need not remember these values. You just remember the shape of the Rayleigh density function. That is enough to write in examinations. So fx of x, and this shape is enough. This shape is enough, and it is a value a, and this is origin. We just remember these values 0, a, x and fx of x. So no need to remember these ones. So this is what about the probability density function of Rayleigh random variable. If you see, the Rayleigh random variable density function is given by 2 by b into x minus a into e power minus x minus a whole square by b for x greater than or equal to a, 0 for x less than a, x less than a. So that is what about the density function. So the density function, next one is the density function. The density function is represented by like this: fx of x is equal to 1 minus e power minus x minus a whole square by b for x greater than or equal to a, 0 for x less than a, 0 for x less than a. So this is the probability distribution function of Rayleigh random variable. So 1 minus e power minus x minus a whole square by b, and 0 for x less than a. So if you plot the same one, so it is like this. Here you take x and it is f, capital Fx of x. So the shape of, I already told you, the shape of distribution function is always a increasing function. So in that case, the shape is like this. So if you put x equal 0 in the x equal a in the above expression, a minus a, that means e power 0. That means 1 minus 1 is equal to 0. You are having at x equal a, it has a value of 0. So that means it starts at a point A on x-axis, and from there onwards it slowly increases. And at the maximum value, at a value of x equal infinity, it has a value of 1. So you should remember, you should represent almost every distribution function like this. It starts its starting point and its ending point. At the ending point, it has a amplitude of what? 1. So why? Because the property of distribution function tells like that. At x equal to infinity, it has a value of 1, and at x equal to it has a value of 0, and it is the origin. This is what about the Rayleigh distribution function and Rayleigh random variable. We have one more random variable, that is Poisson random variable. So the density function of Poisson random variable is given by it is e power minus b into summation k equal to 0 to infinity b power k by k factorial into delta of x minus k, e power minus b into summation k equal to 0 to infinity b power k by k factorial into delta of x minus this is k. So in the same way, the distribution function is given by capital Fx of x equal to only small change. The summations are given, so that is sigma k equal to 0 to infinity b power k by k factorial into u of x minus k. We have already seen that delta means impulse function, u means step function. So fx of x, small fx of x means density function. This is density function, and this one is distribution function. So as the summation is comes, there is no continuous shape for this random variable. If you see the binomial random variable also, there is no shape. I don't draw any shape for binomial random variable. In the same way, for the Poisson random variable also, there is no particular shape. So the shape is depends on the given variables. So here the variables are very important. The variable is b. The important variable is b. It is always equal to 0. And some cases they gave you time duration t, and average rate lambda, average rate lambda. In that case you will write your b is equal to what? Lambda into capital T, lambda into capital T. So the constant b can be written as the multiplication of average rate into the time t, into the time t. So this you have to use if in the problem if they gave you average rate, average rate. Now, what is the application of this Poisson dynamical? So the Poisson dynamical applications are first one, applications. So it is mainly used for counting purpose. Counting purpose. That means so you can find out the electrons emitted from a electron gun electron gun in a given duration. In a given duration. This we particularly remember. So to find out the counting means you should take particular time interval. So that means for that purpose, one time interval is particular compulsorily be taken. So number of electrons emitted from an electron gun, or or number of number of vehicles vehicles coming to coming to coming to petrol bunk in the same way in a given duration. So for timing it is 1 hour or 2 hours or 3 hours, etc. You should take particularly compulsory you should take one time interval. Likewise, so you should these are used to find out the counting purpose. So the these are the applications. So you should remember the applications of Poisson and Bernoulli is for counting purpose. Counting purpose. So this is what about the Poisson and so the Poisson and variable density function is given by f e power minus p summation v power k by k factor into delta of x minus k. If you see the density function always with impulse function, whereas the density function, sorry, distribution function is always with the step function, links with the step function. That point is everyone should remember. Okay, so where the value of b, constant b, that is it is a constant. So constant b is always greater than 0. So that b can be written as lambda into t if time duration and average rate is given. So the applications of Poisson variable is counting purpose. So number of electrons emitted, a number of vehicles coming in the petrol bunk, a number of persons visiting the cinema theater, like that. Everywhere you can number of persons visiting a mall, like that. Everywhere you can find out the counting total number, like that. You can use by using this random variable. So every random variable has one particular application we are using. So with this we completed all types of random variables in the random variable concept. So the next concept we are going to deal with in the next session is that is expectation of a random variable. So the density functions and distribution functions of random variables are very important to do expectation problems in the next session. So please read this density functions and distribution functions very well, so that it will be very helpful in the next sessions. So thank you everyone. So I request all of you to please subscribe Easy BTech channel. Thank you.